Deep in the cosmos lies OJ-287, a colossal pair of black holes that seem to break every rule of time itself. Their dance has puzzled scientists for decades, and what happens next could rewrite what we know about gravity. If this fascinates you, please like, subscribe and share, and tell us in the comments, do you think time can truly be broken? Thank you for watching. Now let's begin. Far beyond the reach of ordinary stars in a quiet region of the constellation, Cancer lies a giant elliptical galaxy that holds within it one of the most extraordinary objects known to science. This galaxy, faint through the lens of small telescopes, is home to OJ-287, a source of flickering light that has drawn attention for more than a century. Its host is an ancient stellar system shaped long ago when galaxies merged and settled into a vast cloud of aging stars. The region around it is sparse, filled with old red suns drifting in elongated orbits and clouds of hot intergalactic gas. There are no bright spiral arms here, no blue clusters of new stars. The environment is massive and subdued, a halo of billions of solar masses formed during the early epochs of the universe. Seen from afar, its outer boundary glows faintly in X-rays, a remnant of the intense energy locked in the motions of gas and dark matter. Within this tranquil sphere, OJ-287 burns with a light that belies its distance, a flicker that carries across billions of light-years, cutting through the background noise of space. The light of OJ-287 does not shine with steady intensity. It wavers and bursts in patterns that repeat across decades, revealing that something powerful lies hidden at the galaxy's center. Most of the galaxy itself remains dark, invisible light, its stars too distant and faint to resolve individually. The glow that astronomers observe comes instead from a single point, a quasar, a kind of cosmic lighthouse, powered by the gravity of a supermassive black hole. Around this invisible heart, gas and dust swirl inward, forming a flattened disk that heats as it falls. Friction between the particles converts motion into light, and the energy released is so immense that it can outshine the entire galaxy hosting it. OJ-287 is one such beacon, its brightness changing in a way that no ordinary star or cluster could explain. When the quasar was first catalogued in the early 20th century, it appeared to be one of many mysterious optical variables. Photographic plates taken at different times showed that its light fluctuated dramatically, sometimes doubling or tripling in brightness before fading again. At first, this was attributed to turbulence within the disk, or random instabilities near the black hole. But as decades passed, astronomers began to notice something unusual. The variations were not random. They seemed to follow a rhythm repeating over long intervals. Such periodicity in a quasar was rare, almost unheard of. It suggested that OJ-287 was not a simple isolated system. The surrounding region of the galaxy provides the setting for this cosmic rhythm. Its gravitational field extends for tens of thousands of light-years, binding countless old stars and clouds of plasma within a single halo. The gas is thin, heated to millions of degrees by shock waves and magnetic turbulence. Observatories sensitive to X-rays detect faint halos around this and other elliptical galaxies, signs of the slow leakage of energy from their cores. At the very center where density and gravity peak, the light of OJ-287 dominates all else. The quasar sits buried deep in this dense core, invisible to direct view, yet the photons it sends forth trace a perfect path through space, carrying information about processes that cannot be observed in any laboratory. Space around the galaxy is calm compared with the inner regions where the quasar resides. At the outer edge, stars move sluggishly, orbiting once every few 100 million years. Dark matter shapes the potential well that holds them, creating a smooth gravitational gradient that funnels matter inward. Closer to the core, the stars become more numerous, and the background light grows. Gas flowing inward compresses under its own weight, heating until it glows. This slow inflow feeds the central black hole, maintaining the energy output that defines the quasar's nature. Yet in OJ 287, something disturbs this balance. The outbursts come in pairs like double heartbeats separated by predictable spans of time. No single process within a disk could account for such precision. The galaxy's position in the cosmic web gives astronomers a clear line of sight to its nucleus. There is little obscuring dust between Earth and Cancer's outer reaches, allowing telescopes on the ground and in orbit to record OJ 287's brightness across the electromagnetic spectrum. When mapped in radio wavelengths, the source appears elongated, suggesting a jet of particles shooting outward from its center. In optical light, the main feature is its rapid variation. Infrared observations reveal the heat of the disk, while X-rays trace the most energetic collisions near the event horizon. Combined, these data show a system operating at the limits of physical possibility, a structure powered by gravity so intense that even time and space are distorted around it. In this context, the galaxy that hosts OJ 287 serves as a quiet backdrop, a cradle for extremes. Its stars, numbering in the hundreds of billions, orbit in silence around the central mass, each a tiny fraction of the whole. Over billions of years, random mergers and gravitational encounters have smoothed its shape into a nearly perfect sphere. All motion eventually bends toward the center, and at the core lies the quasar's twin engines. Even though their light reaches Earth after a journey of billions of years, the information it carries still reflects precise events, flares that were produced before multicellular life appeared on Earth, and yet whose echoes continue to mark the calendars of modern observatories. Astronomers measure the galaxy's distance as several billion light-years, meaning its light began its journey when the universe was younger and galaxies were still forming through collisions. OJ 287 has likely existed in roughly its current state since that epoch. The energy emerging from its nucleus continues to travel outward, unaffected by the vast expansion of space, except for the slow redshifting that stretches its wavelength. Each photon arriving today began its path in a region where gravity bends space-time into a funnel. In that region, all directions lead inward, and only the escaping radiation tells of what lies within. The calm that surrounds OJ 287's host galaxy is deceptive. Beyond its outer halo lies the void where intergalactic gas thins to near-nothingness. The contrast between emptiness and the dense heart of the galaxy defines the scale of this system. Here, physical distances stretch to such magnitudes that a beam of light takes tens of thousands of years to cross from edge to center. And yet within that span, the central region can erupt in hours, bright enough to alter the combined luminosity of an entire galaxy. This is the paradox of OJ 287's environment, immense size and quiet structure, enclosing an energy source that flickers with almost human-scale intervals. The study of this galaxy began with modest instruments, but it has evolved into one of the longest continuous observations in modern astronomy. Generations of observers have compared photographs noting the regular rise and fall in brightness. Each new instrument, from ground-based telescopes to orbital observatories, adds detail to the portrait. The more the galaxy is observed, the clearer it becomes that its quasar is not behaving as expected. The faint host remains steady, but the quasar pulses, sending twin flashes every cycle, an ancient clock running in the depth of cosmic time. Thus the setting is established a vast, quiet, elliptical galaxy in Cancer, holding within it a quasar whose behavior has defied simple explanation for more than a century. The galaxy forms the outermost region of this exploration, a stable shell containing an unstable heart. From this starting point, the journey will move gradually inward from the environment that surrounds OJ-287 toward the structures and forces that drive its mysterious rhythm. When astronomers first recorded the faint glimmer of OJ-287 on photographic plates in the early decades of the 20th century, they could not have known that the object would become one of the most closely studied quasars in the sky. At first, it appeared as a simple point of light, no different from countless others scattered across the star fields of Cancer. Early observers noticed that it was not steady. Some nights it brightened beyond its usual magnitude, and others it dimmed until nearly invisible. These shifts occurred over weeks and months, but the equipment of that era allowed only irregular observations. The fluctuations were logged, yet their meaning remained obscure. It would take generations of patient comparison before a deeper pattern began to emerge. The history of OJ-287 is therefore not only a story of the object itself, but also of human persistence as each decade brought new technology and with it sharper records of a distant and rhythmic universe. By the middle of the century, astronomers using larger telescopes began to recognize OJ-287 as part of a growing class of objects known for their erratic light output. When radio astronomy developed, the source appeared bright at long wavelengths as well. It was identified as a quasar short for quasi-stellar radio source, meaning that it emitted powerful radio waves while appearing point-like similar to a star. At that time, the concept of a supermassive black hole was still new, and quasars were seen as mysterious powerhouses, their energy output surpassing entire galaxies. OJ-287 fit the profile, though its precise distance was not immediately clear. Only later, when redshift measurements were refined, did astronomers realize that the light reaching Earth had traveled for billions of years. The earliest systematic light curves of OJ-287 were constructed by comparing archived photographic plates from observatories around the world. Decades of accumulated images revealed that the brightness changes were not random but followed a recurring cycle. This recognition came slowly. Each observation on its own seemed insignificant, but together they showed a remarkable pattern. Roughly every 12 years, OJ-287 produced two sharp peaks in brightness, separated by about 1 to 2 years. Between these double outbursts, the quasar remained comparatively calm. When plotted, the pattern resembled twin mountain peaks rising from a long, flat plain, a visual signature unlike that of any other quasar known at the time. This was a startling discovery, for quasars were expected to vary chaotically as material swirled into their black holes. Regularity suggested that a stable repeating mechanism was at work. The first explanations proposed that massive clouds within the disk periodically ignited, or that magnetic fields built up and collapsed in cycles, but none of these ideas could account for the double nature of the peaks, or their extraordinary consistency across more than a century of data. The same rhythm appeared again and again, unaltered by time, as if some hidden metronome governed the heart of this distant system. The process of discovery continued through careful observation rather than sudden revelation. As telescopes improved, so did the temporal resolution of the light curve. Astronomers began to predict when the next outbursts would occur and to prepare for them in advance. In the 1970s and 1980s, new optical monitoring campaigns confirmed that OJ-287 indeed erupted on schedule. The timing precision was astonishing. Within a few months' margin of error, each burst arrived as expected, reinforcing the sense that this was not random noise but a predictable cosmic clock. Parallel to optical monitoring instruments sensitive to other wavelengths were pointed at OJ-287. Radio telescopes revealed a core with extended jets stretching across intergalactic distances, while X-ray detectors picked up faint high-energy flares coinciding with optical peaks. These multi-wavelength observations painted a complex picture of a system with many interacting layers. The visible outbursts were only the most accessible signs of deeper events occurring close to the central black hole. What remained unclear was why the flares came in pairs. If one cycle corresponded to a particular process, what produced the second delayed pulse of equal brightness? The answer would not come immediately. For years, the double-peaked pattern was an unsolved curiosity discussed in journals, but without firm consensus. Some speculated that the quasar might contain two separate accretion regions, orbiting a single black hole, each producing its own flare. Others suggested that external clouds of gas might pass through the line of sight in a repeating orbit, but such mechanisms could not maintain regularity over century-long timescales. Something more stable and deeply gravitational had to be involved. The challenge for scientists was to reconcile the observed periodicity with the unpredictable nature of black hole accretion. During this time, astronomers continued to improve the precision of the light curve. By the early 21st century, digital sensors had replaced photographic plates, and continuous monitoring by robotic telescopes provided near-daily measurements. Historical data were digitized, and when combined they formed a record spanning more than 100 years, one of the longest continuous brightness records for any quasar. This long timeline made OJ-287 unique. It was not only a distant light source, but also a record of cosmic timing, offering a window into processes that operate far beyond direct observation. The more complete the data became, the clearer it was that the periodicity held firm. Each cycle included two peaks, the first strong and rapid, the second softer and slightly delayed. Between them the light faded smoothly. The pattern suggested that two separate but related events occurred within each 12-year orbit. It was this precision that hinted at the involvement of two massive bodies moving around one another, a binary black hole system. Though still only a hypothesis at that stage, the idea gained strength because it matched the data in both timing and intensity. If two black holes were orbiting each other, their gravitational interaction could drive periodic disturbances in the surrounding disk, causing twin eruptions of light when one passed through the dense material near the other. By the time the hypothesis of a binary black hole gained acceptance, OJ-287 had become a benchmark for long-term astrophysical study. It was no longer a curiosity but a test case for understanding extreme gravity. Observatories across the world began to coordinate observations, ensuring that no cycle would go unrecorded. Each new outburst was greeted with both excitement and caution, for even a small deviation in timing could challenge the theoretical models. The predicted peaks became opportunities to test physics itself. In 2015, an outburst arrived within days of the calculated date, confirming not only the orbital model, but also the reliability of general relativity under immense gravitational forces. Behind every observation lay the effort of countless nights of monitoring. Automated telescopes scanned the sky, comparing brightness levels and sending alerts when OJ-287 began to brighten. Amateur astronomers joined the campaign, contributing valuable data from small observatories. The quasar became a collaborative beacon, a shared focus for a community spread across continents. Each observer, no matter how small their telescope, contributed to understanding a phenomenon occurring billions of light-years away. Over time, the record of OJ-287's repeating flares became an archive of light that stretched across generations. It served as a rare example of a system whose internal clock could be measured and predicted within human lifetimes. The discovery through flickering light thus transformed from an accident of observation into a precise scientific instrument. Through patience and accumulation, the randomness of distant photons resolved into the rhythm of a binary heartbeat, echoing across cosmic distances. The story of its discovery demonstrates how long observation, careful measurement, and the persistence of curiosity can bring order to apparent chaos, revealing the subtle regularities hidden in the deep time of the universe. A quasar is the visible signature of matter falling into a supermassive black hole. When a distant galaxy's core brightens beyond the combined light of all its stars, it signals that gravitational energy is being transformed into radiation. In OJ-287, that process occurs at scales and energies that defy simple comparison. To understand its behavior, astronomers begin with the general structure shared by all quasars. At the center lies a black hole of enormous mass, its gravity so strong that not even light can escape once it passes a boundary known as the event horizon. Around this void, gas and dust accumulate into a rotating disk. As friction and compression within the disk increase, the material heats to tens of millions of degrees. Photons escape from its surface before crossing the point of no return, and the resulting radiation can be seen across the universe. These emissions make the nucleus of an otherwise dark galaxy shine like a small star through a telescope, though what appears as a single point conceals regions of turbulent plasma stretching across light days of space. OJ-287 is one of many such active galactic nuclei, yet it stands apart because of its peculiar regularity. In most quasars, brightness fluctuates erratically as magnetic fields twist, and gas streams collide near the black hole. The energy release is chaotic, following no schedule. In OJ-287, however, periodic bursts occur with near mechanical precision, implying that some larger system governs the rhythm. The constant behavior of the quasar's outer regions, combined with the repeated pulses at its core, creates a layered structure of calm and violence. The galaxy's stars orbit quietly, the accretion disk glows steadily, and deep within unseen gravitational interactions modulate the light that reaches Earth. The quasar's luminosity comes from the conversion of gravitational potential energy into heat and radiation. As matter spirals inward, it loses angular momentum and falls closer to the black hole. The immense compression raises its temperature to hundreds of thousands of degrees, producing visible light and ultraviolet radiation. Closer still, X-rays are created as electrons and ions collide at near relativistic speeds. Magnetic fields generated within the disk confine this plasma, channeling some of it into narrow jets that emerge perpendicular to the disk plane. These jets carry particles far into intergalactic space at nearly the speed of the light, creating elongated radio structures visible from Earth. The interplay between the disk and the jet defines the outward appearance of a quasar, but the underlying driver is the black hole's mass and spin. In OJ-287, the central black hole is immense. Estimates place it at several billion times the mass of the Sun, making it one of the most massive known in an active system. The gravitational field around such an object extends for hundreds of astronomical units, far beyond the orbit of any planet. Matter drawn inward experiences a slow spiral punctuated by abrupt heating events, as turbulence increases near the inner edge of the disk. The radiation escaping from this region forms the quasar's luminous core, whose brightness can vary by factors of several depending on the rate of infall. The entire mechanism is governed by the physics of general relativity, where time slows and space bends under gravity's influence. A quasar's brightness is not uniform. The outer parts of the accretion disk emit primarily in infrared and optical wavelengths, while the inner regions contribute ultraviolet and X-ray radiation. When telescopes collect light from OJ-287, they capture the integrated emission of all these zones combined with radiation scattered by the surrounding medium. The apparent point-like nature of the source is therefore an illusion of distance. In reality, it is a structure many light days across composed of plasma rotating at nearly the speed of light around an invisible singularity. Understanding such a system requires observations at multiple wavelengths, each revealing a different aspect of the energy flow from the disk to space. Through these observations, astronomers learned that OJ-287 behaves like a blazar, a subclass of quasars whose jets are oriented almost directly toward Earth. When the jet points close to our line of sight, relativistic effects amplify its apparent brightness, a phenomenon known as beaming. This amplification makes even small fluctuations in emission appear as sharp peaks in the light curve. Yet beaming alone cannot explain OJ-287's double outbursts, since orientation effects do not occur on such regular timescales. The beamed jet contributes to the quasar's overall luminosity, but the deeper rhythm must originate within the accretion structure itself. Spectroscopic analysis of OJ-287 reveals the fingerprints of hot gas moving at extreme speeds. Broad emission lines indicate that the material is orbiting at thousands of kilometers per second around the central mass. Subtle shifts in these lines over time provide information about the system's dynamics, hinting at gravitational perturbations that might be caused by a second massive object nearby. Variations in polarization, the orientation of light waves further suggest a changing magnetic environment, consistent with complex motion within the disk. Together, these features portray OJ-287 as a quasar whose central engine is not single and stable, but instead influenced by another massive companion. The concept of a quasar helps clarify why OJ-287 radiates so intensely, but it also underscores how much remains unseen. The black hole itself is invisible. What is observed is the energy released by matter on its way in. The region inside the event horizon remains forever hidden, described only by mathematics. Outside this boundary, everything is dynamic. Gas is heated, particles are accelerated, and radiation escapes into the void. Even at billions of light-years, telescopes can detect these processes because the energy conversion is so efficient. A small amount of matter falling into a supermassive black hole can produce more radiation than millions of stars burning for the same period. OJ-287 in particular demonstrates this efficiency at an astonishing scale. During its outbursts, it brightens enough to outshine its entire host galaxy. Each flare represents an event where an enormous quantity of matter, perhaps several Earth masses, is consumed within days. The light curve records these meals, showing how the quasar flickers as it feeds. Over time, this feeding process shapes the evolution of the host galaxy, influencing star formation by heating and dispersing surrounding gas. Thus, the activity of the quasar is not isolated, but tied to the life cycle of the galaxy that surrounds it. Despite the intense energy released, the overall structure of OJ-287 remains stable. Its accretion disk persists over millions of years, replenished by gas drawn from interstellar space. Magnetic fields thread through the disk and the jets maintaining order within the turbulence. Observations of polarization and spectral shifts indicate that the disk is tilted relative to the jets, suggesting that the system is not perfectly aligned. This misalignment may be a clue to the gravitational influence of a second body, which periodically disturbs the flow of matter and triggers the distinctive flares. Through the concept of the quasar OJ-287 becomes comprehensible as both a natural process and an extraordinary phenomenon. It follows the same physical laws as every other active galaxy, yet within those laws it finds a rare balance between order and chaos. The quasar converts gravity into light time, into rhythm and distance, into measurable signals. Understanding it begins with the recognition that every photon reaching Earth has escaped from the edge of a region where space-time itself is curved almost beyond imagination. Each cycle of brightness tells of a system that endures through billions of years, governed by forces that remain constant even as the universe expands around it. In this way, OJ-287 serves as a bridge between observation and theory. Its visible light provides data. Its periodicity points toward deeper structures yet to be explored. The nature of a quasar luminous, distant and persistent is fully embodied here, but beneath its surface lies a second mystery. The quasar's behavior suggests that there may be not one black hole but two locked in an orbit so tight and so massive that it distorts time itself. To reach that conclusion, the next step moves from describing what a quasar is to understanding why this particular one refuses to behave like any other. Among the hundreds of known quasars scattered across the observable universe, OJ-287 alone displays a rhythm so precise that its light curve can be predicted years in advance. Each sequence unfolds in pairs with two major peaks, separated by about 1 to 2 years, and these pairs themselves return every 12 years with a consistency that challenges the chaotic nature of accretion. This unusual periodicity drew scientists toward an inevitable question. What kind of mechanism could maintain such timing across more than a century of observation? The search for an answer began with the simplest hypotheses and advanced toward those involving the most extreme gravitational systems known. What emerged from that process was a story not of random eruptions but of celestial motion, an unseen dance between colossal masses bound by gravity's most exacting rules. Early interpretations sought explanations within the behavior of a single supermassive black hole. Some proposed that periodic instabilities within the accretion disk might cause matter to pile up and collapse in repeating intervals. Others speculated that the disk itself could wobble or precess periodically aligning its bright inner regions with Earth's line of sight, creating apparent flares without changes in actual energy output. Yet none of these models could reproduce the double nature of the flares or their stable timing. If the system were driven by internal turbulence, the cycles would drift over time, losing coherence. But the record of OJ-287 showed no such drift. Each pair of peaks recurred at nearly the same interval for more than 100 years, suggesting an external orbital cause. By the 1980s, astronomers began to test the possibility that OJ-287 might contain two black holes instead of one. Binary systems are natural outcomes of galaxy mergers, and elliptical galaxies like the one hosting OJ-287 are thought to form through such mergers in the early universe. When two galaxies combine, their central black holes sink toward the new center, gradually spiraling together through friction and gravitational wave emission. This process can take millions of years, during which the pair remains bound in orbit. If one of those black holes carries an accretion disk, the motion of the other could periodically disturb it, producing the kind of regular brightening seen in OJ-287. The hypothesis fit the data elegantly. Two bodies immense and invisible, locked in a gravitational relationship that played out in cycles of light. The periodicity's precision implied a massive primary and a smaller companion in an eccentric orbit. As the secondary black hole swung close to the primary, it might plunge through the outer edge of the accretion disk, heating the gas and generating an enormous outburst of light. About a year later, as it completed its passage through another part of the disk, a second flare would occur, explaining the paired peaks. Once the secondary moved outward again, the system would return to quiescence until the orbit brought it back. This model not only matched the pattern of outbursts, but also predicted subtle shifts in timing caused by general relativity, a testable feature that later observations would confirm. At first, the notion of two black holes interacting in this way seemed almost too precise to be real. Yet the growing dataset from optical telescopes, radio observatories, and space-based instruments supported it. When scientists calculated the expected orbital parameters, they found that the primary black hole must be extraordinarily massive, billions of times the mass of the Sun, while the secondary likely measured tens of millions. The orbit's period of 12 years and its high eccentricity fit the observed intervals perfectly. Moreover, the model explained why the peaks did not appear at exactly the same brightness or spacing. Each cycle relativistic effect slightly altered the secondary's path as spacetime itself warped under the combined gravity. The binary hypothesis also accounted for the remarkable longevity of the pattern. Because the secondary's orbit decays slowly through the emission of gravitational waves, the system evolves at a pace that allows astronomers to observe its changes over human timescales. The tiny adjustments in timing from cycle to cycle become a natural clock for testing Einstein's equations in the strong gravity regime. When new outbursts occurred at the predicted times, it reinforced confidence that the underlying mechanism was orbital rather than random. The precision became so reliable that astronomers could forecast future flares with a margin of error measured in days, an extraordinary achievement for a system billions of light-years away. Periodic quasars are exceedingly rare, which makes OJ-287 a unique laboratory for astrophysics. In a universe where most luminous cores flicker unpredictably, here is one that behaves like a celestial pendulum. The periodicity extends beyond simple brightness. It shapes the polarization and spectral properties of the quasar as well. During each outburst, the optical spectrum shifts toward higher energy, consistent with sudden heating of disk material. Radio observations show corresponding spikes, suggesting that the jet responds almost immediately to disturbances in the accretion flow. Such synchronization across wavelengths hints at a single physical event affecting the entire system, rather than separate random flares. The concept of periodicity in OJ-287 reveals how time operates differently under gravity's influence. In ordinary systems, orbits follow predictable paths described by Newton's laws, but in a binary system dominated by a black hole of billions of solar masses, spacetime itself bends, and the secondary's orbit processes rotating gradually around the primary in a motion first described by general relativity. This precession shifts the points where the secondary crosses the disk, changing the exact moment of each impact. By measuring these shifts, astronomers effectively watch spacetime curvature in action, confirming Einstein's predictions on scales far beyond the solar system. Each repetition of the double flare serves as both a beacon and a measurement. The first outburst marks the moment when the secondary plunges through the disk's near side. The second corresponds to its passage through the far side. Between these events, gas disturbed by the impact continues to glow, and shock waves propagate through the disk, gradually fading as the system settles. Over the next decade, the orbit carries the secondary outward before gravity draws it back again. The light reaching Earth from these collisions has travelled for billions of years, yet it still records the precise geometry of the orbit as it existed long before humanity evolved. In this sense, OJ-287's periodicity is not merely a curiosity but a bridge across time. The photons observed today began their journey when the Milky Way was still forming its spiral structure. The system's consistency over such spans reveals the stability of physical laws themselves. Gravity, radiation, and motion obey the same equations whether in the solar system or at the edge of the observable universe. The repeating pattern of OJ-287 confirms that the cosmos operates with reliability even at its most extreme scales. Through decades of study, the quasar's rhythm has remained one of the most convincing pieces of evidence for a binary black hole system in nature. Each cycle reinforces the interpretation that two enormous masses are bound together in a gravitational dance whose music is light. The recognition of this periodicity transformed OJ-287 from an oddity into a cornerstone of modern astrophysics. What began as flickering on photographic plates now stands as a precise chronometer of cosmic motion. The pattern's regularity not only explains the behavior of this single quasar, but also opens the path to identifying other binaries hidden among the universe's distant lights. As the story of OJ-287 unfolds, the rhythmic pulses continue marking the seconds of a clock that measures both gravity and time on a scale beyond imagination. The persistent regularity of OJ-287's light has been revealed not through a single observation, but through more than a century of patient watching. Few astronomical objects have been monitored for so long, and none with such precision across so many instruments and eras. From the first faint notations on glass photographic plates to modern digital sensors capturing photons with millisecond accuracy, the record of OJ-287 forms a continuous thread that ties generations of astronomers together. The earliest photographs, often taken for other purposes, preserved accidental glimpses of the quasar's brightness, their value recognized only decades later when long-term trends became visible. By comparing these plates, researchers reconstructed a timeline of outbursts reaching back to the late 19th century. Each new generation added a layer of detail, and the pattern that emerged has remained astonishingly stable, a pair of bright flares roughly every 12 years, persistent through wars, technological revolutions, and the entire modern history of astrophysics. The method of long-term monitoring depends on consistency more than power. A single telescope, however advanced, cannot track a variable object for a century, so the task has passed from one observer to the next, forming an unbroken collaboration across time. Amateur astronomers, university observatories, and international surveys all contribute data. Every clear night, telescopes, small and large, record the quasar's brightness in multiple filters, measuring tiny variations in magnitude that together trace the heartbeat of a distant galaxy. The sheer continuity of this project is remarkable. Light that left OJ-287 billions of years ago is captured by instruments spread across the Earth, its faint variations aligning perfectly with those detected by predecessors long deceased. The process of extracting a precise light curve from these scattered observations requires careful calibration. Each instrument has its own sensitivity, each detector its own bias, and the atmosphere itself introduces noise. By standardizing these measurements, astronomers create a unified record that transcends the limitations of any single data set. The result is a curve so smooth and regular that even small deviations carry meaning. When the brightness begins to rise, observatories around the world take notice. Alerts circulate, triggering concentrated campaigns across wavelengths, optical, radio, infrared, X-ray to capture every phase of the event. The coordination of such efforts illustrates the global scale of modern astronomy, with observatories in different time zones ensuring that the quasar is never unobserved. This meticulous record has transformed OJ-287 into one of the most valuable natural laboratories for studying both black holes and relativity. The century-long timeline allows scientists to test whether the intervals between flares remain constant or change subtly as energy is lost to gravitational waves. Small discrepancies between predicted and observed timings provide evidence for orbital decay. Indeed, the latest cycles show that the peaks arrive slightly earlier than expected, by purely Newtonian models matching precisely the corrections predicted by general relativity. Few other systems permit such direct measurement of space-time curvature through long-term observation. OJ-287 has thus become both a chronicle of light and a measurement of time itself. The historical record also reveals variations within each cycle that help refine understanding of the system. The first flare of each 12-year pair is usually brighter and sharper, rising over weeks and fading in months, while the second is slower and more gradual. This asymmetry reflects differences in the regions of the accretion disk where the impacts occur. The first plunge of the secondary black hole likely happens closer to the disk's dense center, producing a more intense flash, while the second crosses through outer cooler regions. The difference between them provides insight into the temperature and density structure of the disk data that would be otherwise impossible to obtain at such distances. Throughout the 20th century, OJ-287's reliability helped shape theories of how galaxies evolve. The discovery of its repeating cycle encouraged astronomers to search for similar periodicities in other quasars, though few were found. Those that did show hints of regular variation often lacked sufficient data to confirm it. The completeness of OJ-287's record made it an archetype showing that under certain conditions, binary black holes can reveal themselves through predictable light. Its behavior inspired a new class of observational programs dedicated to long-term monitoring, emphasizing patience and precision over immediate results. The transition from photographic plates to electronic detectors in the latter part of the century brought a leap in accuracy. Charged coupled devices, or CCDs, could measure brightness with unprecedented sensitivity, capturing subtle fluctuations invisible to the human eye. These instruments allowed scientists to track OJ-287 nightly, building a near-continuous sequence of data points. The resulting light curve shows not only the grand 12-year pattern, but also smaller variations on timescales of days and hours, evidence of turbulence and magnetic activity near the event horizon. Such fine structure enriches the picture, revealing a dynamic environment where large-scale periodicity coexists with constant microscopic motion. Space-based observatories further expanded the view. Telescopes sensitive to infrared and X-rays confirmed that OJ-287 emits across the entire electromagnetic spectrum. The infrared light traces the warm outer disk, while X-rays record the immediate aftermath of impact events when gas is heated to millions of degrees. Even gamma-ray bursts have been detected, signaling that particles in the jet are accelerated to near light speed. By combining these data, scientists assemble a complete timeline of each cycle, from the first hint of rising brightness to the gradual decline into quiescence. Every wavelength contributes a different perspective, and together they confirm the same regular rhythm first glimpsed on fragile glass plates more than a century ago. The study of OJ-287 also reflects the evolution of scientific collaboration. In the early decades, individual astronomers worked largely in isolation, each producing small fragments of the puzzle. Today, the effort spans continents, involving professional observatories and citizen scientists alike. Data are shared openly, models tested collectively, and predictions refined in real time. When an outburst is anticipated, telescopes from Chile to Finland to India point toward Cancer's faint constellation, each recording the same photon stream as it reaches Earth after a journey of billions of years. This coordination ensures that no moment of the cycle goes unrecorded, and that every deviation is quickly recognized and analyzed. Through this long record, OJ-287 has provided more than a pattern. It has offered evidence for phenomena that cannot be replicated anywhere else. The precession of the secondary's orbit, the release of gravitational waves, and the gradual decay of the orbital period are all measurable through the timing of its flares. Each generation of observers refines the parameters, further reducing uncertainty until the model fits within days. When the most recent flare arrived almost exactly on schedule, It confirmed both the durability of Einstein's equations and the discipline of the astronomers who tested them. The quasar, though remote and ancient, has become a collaborator in humanity's effort to understand gravity's deepest nature. The light of OJ 287 tells not only the story of its own system, but also the story of human observation stretched across time. It links the earliest era of photographic astronomy with the digital precision of the present. The same light that darkened glass plates in the 19th century now triggers detectors orbiting Earth, and both record the same cosmic heartbeat. In its steadiness lies a lesson about persistence, how the slow accumulation of data can reveal truths invisible to any single observation. The long-term monitoring of OJ 287 exemplifies the quiet patience that astronomy demands, where understanding grows not from sudden insight, but from the deliberate watching of light that has travelled billions of years to tell its story. The binary black hole hypothesis for OJ 287 became more than speculation when detailed calculations began to reproduce its light curve with remarkable accuracy. The model proposed that a massive primary black hole weighing billions of times the mass of the Sun was orbited by a smaller companion of several tens of millions of solar masses. Their orbit elongated and tilted relative to the accretion disk brought the secondary close enough every 12 years to pierce the disk twice per orbit, each passage creating an enormous release of light. The precision of this model was immediately compelling, yet it also demanded rigorous testing. For a system so distant, direct imaging of the black holes was impossible. All verification had to come from timing the predictable arrival of flares, each acting as a clock tick echoing across cosmic time. When the model correctly forecast the 1994 outburst, and again the 2005 and 2015 peaks within days, it solidified OJ 287 as one of the most extraordinary confirmations of relativity in the universe. The orbit of the secondary black hole is not a perfect ellipse. It precesses, meaning that the point of closest approach slowly rotates over time due to the intense curvature of space-time near the primary. This precession alters the exact moments when the secondary crosses the disk, shifting the flares slightly earlier or later from one cycle to the next. By measuring those shifts, scientists can calculate the relativistic effects acting on the orbit. The data show that the precession rate is immense, tens of degrees per orbit, far greater than anything observed in smaller systems like Mercury's orbit around the Sun. This is space-time visibly twisting under gravity's pressure, a laboratory of general relativity that operates at energies far beyond human reach. Each flare marks the instant when gravitational geometry becomes light. The structure of the orbit is extreme. The secondary spends most of its 12-year cycle far from the disk, moving through relatively empty space within the gravitational field of the primary. As it nears periapsis, its velocity accelerates to a significant fraction of light speed. The plunge through the accretion disk happens within hours, compressing and heating the surrounding gas. The energy liberated in that collision is enormous, billions of times greater than the total power output of the Sun, and it produces a burst of radiation across the electromagnetic spectrum. When the secondary emerges on the far side, it drags with it streams of disrupted material that spiral back toward the disk, creating a complex interplay of shocks and turbulence that sustain brightness for months. The primary black hole, though stationary relative to the system's center of mass, is not unaffected. The gravitational influence of the secondary distorts its accretion disk, creating waves that ripple outward like tides on an ocean of plasma. These waves alter the distribution of matter and magnetic fields, gradually reshaping the disk's geometry. Over time, these disturbances may even influence the orientation of the jet that extends from the system's poles, causing subtle shifts in its direction. that can be traced through changes in the quasar's radio emission. Thus, each orbit of the secondary does more than trigger two flares. It slowly sculpts the entire inner environment of OJ-287. To capture these processes, astronomers employ detailed computer simulations that model both gravity and fluid dynamics. The calculations include not only Newtonian motion, but also relativistic corrections that describe how time and space bend near massive objects. These simulations show how the secondary black hole plunging through the disk at near relativistic speeds compresses matter into shock fronts and sends jets of gas spiraling outward. The sudden heating raises temperatures to millions of degrees, explaining the observed bursts of X-rays and gamma rays that accompany the optical flares. The models also reveal that after each passage the disk slowly returns to equilibrium, setting the stage for the next cycle. In this sense, the entire system behaves like a cosmic heartbeat, its rhythm maintained by gravity's most fundamental laws. The binary configuration also explains OJ-287's extraordinary luminosity. Most quasars are powered by single accreting black holes whose brightness fluctuates according to the availability of infalling material. In OJ-287, the periodic intrusions of the secondary continually stir the disk, ensuring a steady supply of fresh gas toward the center. Each impact acts as both disruption and renewal, preventing the disk from stabilizing completely and maintaining the quasar's activity over immense spans of time. This ongoing disturbance may be why OJ-287 remains active while other galaxies of similar age have faded into quiescence. The binary partnership keeps the engine alive. Observations confirm that the binary's behavior aligns closely with predictions derived from general relativity. The timing of flares follows equations that account for time dilation, gravitational redshift, and orbital decay due to gravitational wave emission. These effects, minute in human terms, accumulate across centuries, shifting flare timings by measurable amounts. Each new observation adds another data point that either strengthens or challenges the model. So far, all evidence supports it. The orbit is shrinking slowly as the system loses energy. To gravitational waves, ripples in space-time first predicted by Einstein and directly detected by observatories like LIGO in stellar-scale events. OJ-287 represents the same phenomenon on a supermassive scale, though its waves are too low in frequency for current detectors. Future instruments may one day sense them, directly confirming not only the binary's existence, but also its influence on the fabric of the cosmos. The gravitational relationship between the two black holes is balanced yet delicate. Despite their masses, they remain distinct entities rather than merging immediately. The enormous scale of the orbit, spanning hundreds of billions of kilometers, ensures that the secondary completes thousands of revolutions before coalescence occurs. During each orbit, tidal forces act on both bodies, transferring energy and angular momentum. Over millions of years, these interactions will bring the two black holes closer until they spiral into one another, releasing a final burst of gravitational waves before merging into a single, even more massive object. But from Earth's perspective, that end lies far in the future. For now, the binary continues its measured dance, the steady rhythm of light reflecting the unseen motion of mass. Understanding the binary nature of OJ-287 has implications beyond one system. It demonstrates how massive galaxies evolve after mergers, showing that supermassive black holes do not immediately combine but orbit for eons, shaping their environments through gravitational and radiative feedback. The study of such systems helps explain how galaxies regulate their growth and why some remain active long after their peers have dimmed. OJ-287 thus serves as both a test of physics and a record of cosmic history, a snapshot of a process that may one day occur at the center of our own Milky Way, if it merges with the Andromeda Galaxy. Through the binary model, this strange regularity of OJ287 transforms from mystery into predictable order. Each flare, once an unexplained spark, now marks a specific point in a vast orbital cycle, governed by gravity, relativity, and time. The system's endurance across billions of years underscores the permanence of physical law, while its visibility across such distance reveals the power of observation. Two invisible masses locked together in an ancient dance continue to send their rhythm through the darkness, and with every arrival of light on schedule, the hypothesis gains strength, illuminating both the cosmos and the precision of the human mind that measures it. At the center of OJ287, the balance between the massive primary and its smaller companion creates a gravitational environment so extreme that even light bends around it in measurable ways. The primary black hole is estimated to have a mass of nearly 18 billion suns, placing it among the most massive ever inferred. The secondary, though much smaller, is still a giant by any standard, with a mass comparable to tens of millions of suns. Together they form a system that compresses unimaginable mass into a volume smaller than our solar system. The scale of their interaction defines the dynamics of the quasar's light, for each orbit of the secondary sends gravitational ripples through the dense plasma surrounding the primary. The enormous difference in mass creates a relationship of control and disturbance. The primary governs the system's structure, while the smaller companion injects periodic chaos that momentarily transforms order into light. At such masses, gravity no longer behaves as simple attraction, but as a reshaping of space-time itself. The orbit of the secondary traces not a closed ellipse, but a precessing spiral, its trajectory curving in ways that only general relativity can describe. The secondary's path takes it deep into the gravitational well of the primary, where time slows relative to distant observers. From Earth, these distortions manifest as subtle changes in the timing and intensity of flares. Each time the secondary approaches the disk, its motion is altered by the curvature of space-time. The energy released when it pierces the disk depends on both velocity and angle, and no two impacts are exactly alike. The resulting variation is not irregularity but precision, an encoded record of how gravity warps time at the threshold of a black hole. The primary's immense mass defines the surrounding region known as the sphere of influence, within which its gravity dominates the motion of all matter. Gas clouds drawn inward settle into a rotating accretion disk, extending for light days across. This disk is composed of ionized hydrogen-helium and heavier elements stripped of electrons by heat and radiation. The matter within it orbits at speeds that approach a significant fraction of light, with temperatures rising toward the inner edge until radiation pressure balances gravity. Near the event horizon, magnetic fields twist the charged particles into filaments that radiate across the electromagnetic spectrum. Yet despite these ferocious conditions, the disk remains stable enough to persist for millions of years, replenished by slow inflow from the galaxy's interstellar medium. The steady glow it emits is punctuated only when the secondary passes through, transforming gravitational motion into observable brilliance. When the smaller black hole plunges through the disk, the collision is not a direct impact, but a gravitational disturbance that compresses and heats the surrounding gas. The sudden rise in temperature causes the material to emit an intense burst of light. In a few hours, the luminosity of the entire galaxy increases dramatically, peaking as energy radiates outward in optical infrared and X-ray wavelengths. The passage also creates cavities within the disk voids that gradually close as new material spirals inward. The aftermath is turbulent. Shock waves propagate through the plasma, magnetic fields reconnect, and the outer layers ripple like water disturbed by a falling stone. Over weeks, the brightness declines as the disk cools and the secondary recedes. Months later, a second flare emerges when the orbit brings the secondary through another section of the disk, producing a smaller but distinct pulse. This recurring pattern forms the double-peaked light curve that defines OJ-287's rhythm. The violence of these encounters is balanced by the regularity of their occurrence. Each passage follows predictable physics governed by orbital mechanics and relativity. The energy released during a disk crossing depends on the local density of matter, the relative velocity, and the geometry of the orbit. Though each flare differs slightly, the overall pattern remains consistent. Computer models replicate these events in detail, showing how the smaller black hole punches through layers of gas, compressing them into shock fronts, before emerging with a trail of heated material behind it. The simulations reveal that the resulting outburst can last for months, with the brightest emission coming from gas that reaches tens of millions of degrees Celsius. These calculations align with the observed spectrum, confirming that the flares are indeed impact events and not random instabilities. The gravitational dominance of the primary shapes not only the disk but also the flow of time itself. Near the event horizon, 1 minute for a particle in orbit might correspond to hours for an observer far away. This time dilation affects how light from the inner disk appears when viewed from Earth. Photons climbing out of the gravitational well lose energy, shifting toward longer wavelengths. This redshift, combined with the relativistic beaming of the jet aimed partly toward our planet, creates the characteristic spectrum of OJ-287. It is a mixture of signals from multiple regions, each governed by different local times. The flares produced by the secondary occur within this complex background, meaning that their apparent duration and brightness are shaped as much by relativity as by physical impact. The mass difference between the two black holes also dictates how their mutual gravity influences the surrounding galaxy. The combined system emits a slow rain of gravitational waves, ripples in spacetime generated by their orbital motion. Though these waves are far below the frequencies detectable by current instruments, their existence can be inferred from changes in orbital period. Over successive cycles, the secondary's path shortens slightly as energy radiates away. The effect is subtle, measured in tiny advances of the flare schedule, but it confirms that even at intergalactic distances, gravitational waves carry real measurable influence. Future space-based detectors operating at lower frequencies may one day capture these emissions, directly transforming OJ-287 into the first known supermassive binary, detected by gravitational radiation alone. The inner structure of the system, where the disk orbit and jet converge, remains beyond the reach of direct imaging, but its effects are written in light. Spectroscopic studies show that the polarization of OJ-287's radiation changes in sync with the predicted orbital cycle, revealing that the orientation of the magnetic field evolves as the secondary passes. These changes likely reflect the reconfiguration of magnetic lines around the impact zones, a process that also influences the collimation of the jet. When the secondary perturbs the disk, the magnetic field lines anchored in the plasma shift, slightly adjusting the direction of the jet and momentarily altering its brightness. This interplay connects the smallest observable features of the quasar's light with the larger structures extending thousands of light-years into intergalactic space. Inside the orbit of the secondary, the gravitational field is an ocean of curves and eddies. No stable orbits exist close to the primary. Everything that ventures too near is drawn inward. The secondary skirts this boundary, with every approach threading a path between stability and collapse. Its survival across countless revolutions testifies to the precision of its trajectory, balanced on the edge of cosmic annihilation. For observers on Earth, this motion is invisible, but its signature is unmistakable in the timing of the flares. Each crossing marks another completed orbit, another passage through warped space-time. It is an event both violent and predictable, a pulse in the cosmic heartbeat that continues without pause through eras of human history. Thus, the massive primary and its spiraling companion form a relationship of immense scale and delicate timing. Their combined mass bends the surrounding space-time into a gravitational well deeper than any other known active galactic nucleus. The light that escapes from their interactions carries with it the imprint of forces that shape the universe itself. The magnitude of OJ-287's primary ensures that time flows differently there, while the persistence of its secondary ensures that the rhythm continues. Together they define the architecture of the system, one as the steady heart, the other as the moving hand that marks the passage of cosmic time. When the smaller black hole of OJ-287 approaches the dense disk surrounding the larger one, it enters a region where gravity and matter interact in ways that push the limits of known physics. The accretion disk, a flattened ring of plasma orbiting the primary, is not a smooth structure but a turbulent sea of rotating gas. Its particles move at speeds approaching light, colliding and radiating as they spiral inward. Temperatures in the inner regions climb to millions of degrees, while magnetic fields thread through the plasma like invisible ropes, guiding streams of charged particles into the jets that shoot outward from the poles. Within this disk, everything is in motion, orbiting, heating, twisting. Yet from a distance, its light appears calm and continuous. Only when the secondary intrudes does the quiet equilibrium break. The passage of the secondary through the disk is a moment of catastrophic transformation. As it plunges through the dense plasma, it compresses the gas ahead of it, generating shock waves that propagate through the surrounding material. The energy released by this impact is so vast that it momentarily rivals the total output of an entire galaxy. The temperature spikes, the disk glows fiercely, and radiation floods outward across the electromagnetic spectrum. The flare lasts for weeks before gradually fading as the disturbed gas cools and settles back into orbit. Each such event marks one of the paired peaks in OJ-287's recurring cycle. First, when the secondary enters the disk, and again when it exits on the far side. The physics of these impacts is complex but well understood through simulations. As the secondary nears the disk, its gravitational field begins to draw gas toward it, forming a temporary envelope of heated plasma. When it collides with the disk plane, this envelope interacts violently with the surrounding matter, creating temperatures of millions of degrees and producing bursts of X-rays and ultraviolet light. Some of the gas is captured by the secondary, forming a brief accretion disk of its own that glows before dissipating. The rest is ejected outward in expanding shells, adding to the quasar's visible brightness. Because the secondary crosses the disk at high velocity, these emissions occur in a sharp, distinct burst rather than a prolonged outflow. The structure of the accretion disk determines the nature of the flare. The disk of OJ-287 is immense, extending for hundreds of billions of kilometers, with density and temperature increasing toward the center. The inner regions radiate most of the visible light, while the outer portions glow in infrared. When the secondary plunges through, it disrupts not only the local gas but also the magnetic fields that help channel matter inward. The resulting turbulence alters the flow pattern for months afterward, causing secondary fluctuations in brightness as the disk stabilizes. The radiation from these processes carries information about the disk's structure. The speed of cooling, the wavelengths of emitted light, and the duration of the flare all reveal conditions near the event horizon of the primary. Observations during outbursts have confirmed that OJ-287 brightens simultaneously across multiple wavelengths, from optical to X-ray, indicating that the entire disk reacts almost instantly to the disturbance. This synchronization implies that the energy release is not confined to a small region, but distributed through magnetic and radiative coupling across vast distances. The intensity of the flare gradually declines, leaving behind an altered disk whose inner regions have been heated and reshaped. After months of recovery, the quasar returns to its baseline luminosity, remaining steady until the next orbital passage begins the process anew. For astronomers, each flare provides an opportunity to study conditions that cannot be replicated anywhere else. During the 2015 and 2021 outbursts, telescopes around the world observed OJ-287 continuously capturing data in optical, infrared, ultraviolet, and X-ray bands. The results confirmed predictions of both timing and spectral behavior. As expected, the flare began with a rapid rise in brightness, peaking over several days, followed by a gradual decline. The X-ray emission lagged slightly behind the optical peak, consistent with shock heating and subsequent cooling. The polarization of the emitted light rotated in a pattern that matched theoretical models of a disk disturbed by a passing massive object. Each of these observations strengthened confidence in the binary impact model, demonstrating that theory and data converge even across billions of light years. The impact events also provide insight into the nature of the accretion disk itself. Under normal circumstances, disks around supermassive black holes evolve slowly their viscosity, determining how quickly matter drifts inward. In OJ-287, however, the repeated intrusions of the secondary accelerate this process. Each crossing mixes layers of plasma that would otherwise remain separate, redistributing angular momentum and altering density profiles. This continual stirring may explain why OJ-287 remains so luminous compared with similar quasars of the same age. The system is effectively self-renewing its periodic collisions, injecting new energy that prevents the disk from becoming dormant. The material within the disk follows predictable physical laws, but near the black hole, conditions blur the boundary between classical and relativistic physics. Gas orbiting close to the event horizon experiences time differently depending on its distance from the center. To an external observer, motion near the horizon appears to slow, while to the particles themselves processes unfold normally. The radiation that escapes carries the imprint of this distortion. Spectral lines are broadened and redshifted, revealing that gravity stretches the wavelength of light as it climbs out of the potential well. During a flare, the emission from newly heated gas shows additional broadening evidence of both relativistic speed and gravitational influence. These features provide one of the few direct tests of how light behaves in the strong gravity regime. When the secondary leaves the disk and continues along its orbit, it carries with it a wake of disturbed gas that gradually falls back toward the primary. This returning material can trigger smaller delayed flares as it collides with the surrounding plasma. These aftershocks, visible as minor ripples in the light curve, further confirm that the major outbursts are genuine physical impacts rather than distant illusions. The recurrence of both major and minor flares with predictable timing creates a portrait of a system in perpetual motion, its vast energies balanced by the precise rhythm of its orbital mechanics. Each passage through the disk not only produces light, but also influences the gravitational structure of the system. As the secondary interacts with the dense matter, it experiences a drag that alters its velocity slightly. Over millions of years, these tiny changes accumulate, causing the orbit to contract and its period to shorten. The gradual acceleration of the flare schedule observed as each new cycle arriving slightly earlier than the last reflects this decay. The loss of orbital energy through both gravitational radiation and disk interaction ensures that the two black holes will eventually merge, though that event lies tens of thousands of years in the future. For now, the system remains stable, repeating its luminous pattern with a constancy that makes it one of the universe's most reliable natural clocks. In observing these violent yet predictable collisions, astronomers glimpse the boundary between order and chaos. The impacts are cataclysmic on a scale beyond comprehension, yet they unfold with mechanical precision dictated by the geometry of space-time. OJ 287 thus reveals not only the destructive power of black holes, but also their capacity for harmony, a cosmic system where periodic violence gives rise to enduring structure. Each flare, though brief, is a message from a realm where gravity and energy trade places where matter becomes light, and where time itself bends to the rhythm of orbiting giants. The impact flares of OJ 287 are not random explosions, but the measured breathing of a system that has persisted for billions of years, its light crossing the universe to record with perfect regularity the quiet pulse of creation and collapse. The system of OJ 287 offers one of the clearest natural laboratories for testing the predictions of general relativity, because its immense scale and precise timing allow even subtle distortions of spacetime to become measurable. In the environment near the primary black hole, gravity is so strong that Newtonian mechanics cannot accurately describe motion or time. The orbit of the secondary precessing and slowly decaying reflects these relativistic effects directly. Every observed flare is not just a burst of radiation, but also a timestamp recording how the geometry of spacetime has shifted since the last cycle. By comparing the timing of outbursts over more than a century, scientists have been able to confirm with astonishing precision that OJ 287 behaves exactly as Einstein's equations predict. The most important measurable phenomenon is orbital precession, the gradual rotation of the secondary's orbital ellipse within the plane of motion. In classical physics, such an orbit would repeat identically with each revolution. Under relativity, however, the immense mass of the primary distorts the surrounding spacetime, causing the point of closest approach to advance with every cycle. In the OJ 287 system, this precession is enormous, roughly 39 degrees per orbit, meaning that each 12-year cycle takes place along a slightly shifted trajectory. This change alters where and when the secondary intersects the accretion disk, producing corresponding shifts in the timing of the double flares. When astronomers accounted for this precession, the predicted arrival of flares matched observations within days, an alignment so precise that it stands as one of the most convincing large-scale tests of general relativity ever achieved outside the solar system. Another key prediction concerns gravitational radiation. As two massive bodies orbit each other, they emit gravitational waves, ripples in the fabric of spacetime that carry energy away. For systems with masses like those of OJ 287, this loss is slow but cumulative. Each orbit removes a minute fraction of the total energy, causing the period to shorten over time. The effect is tiny on human scales, but because OJ 287's flares act as reliable markers, even these infinitesimal changes can be detected. By comparing flare timings across more than a century, researchers have measured the decay rate of the orbit and found it to agree with theoretical expectations for gravitational wave emission. The results confirm that energy is indeed leaving the system in the form of space-time, ripples, the same phenomenon detected by instruments like LIGO on smaller stellar mass scales. OJ 287's environment also provides evidence for relativistic beaming and time dilation, as the secondary races around the primary at a significant fraction of light speed. Radiation from gas surrounding it is compressed in the direction of motion, increasing its apparent brightness to distant observers. Meanwhile, processes occurring near the event horizon unfold under extreme time dilation to an external observer motion. Near the black hole's surface appears to slow, though locally time passes normally. These effects combine to shape the observed light curve. The first flare in each pair appears sharper and brighter, not only because of the density of the disk, but also because of relativistic boosting when the secondary is moving toward Earth. The second flare occurring as it moves away appears softer, and delayed its radiation redshifted by both velocity and gravity. Together they form a pattern that encodes the relativistic behavior of matter in curved space-time. To interpret these details, scientists build models incorporating the full complexity of general relativity, not merely as correction factors, but as fundamental geometry. These models treat space-time as a dynamic stage on which energy and mass reshape the coordinates of motion themselves. In this framework, the orbit of the secondary is not a simple path through space, but a line woven through curved space-time twisting under its own gravity and that of the primary. When data from OJ-287 are plotted against these models, the match is remarkable. Each new flare validates parameters such as the primary's spin, the shape of its gravitational field, and the rate of orbital precession. The precision achieved rivals that of experiments within the solar system, but it occurs on scales billions of times larger, proving that relativity holds universally. The enormous precession of OJ-287's orbit also provides indirect information about the spin of the primary black hole. A rotating black hole drags the surrounding spacetime with it, a phenomenon known as frame dragging. This effect subtly alters the orbit of the secondary, causing additional precession that depends on the spin rate and orientation of the primary. By measuring how much the flare timings deviate from what would be expected for a non-rotating black hole, scientists can estimate this spin. Current analyses suggest that the primary in OJ-287 rotates at a high but submaximal rate, spinning several times per day when scaled to the size of its event horizon. This rotation shapes the orientation of the jets, influences how matter accretes, and determines how efficiently the black hole converts gravitational energy into radiation. Beyond orbital motion, the flares themselves reveal relativistic effects in the emitted light. During outbursts, photons escape from regions deep within the gravitational field, where light paths are bent by curvature. Some rays travel directly toward Earth, while others curve around the black hole before escaping, arriving slightly delayed. This produces subtle echoes in the light curve, faint ripples superimposed on the main flare. Such echoes provide additional confirmation of light bending, a phenomenon first predicted a century ago and now observed in detail at cosmic scales. The polarization of the radiation also rotates in step with the changing gravitational field, further confirming that the quasar's light interacts with space-time geometry as it travels outward. While these observations confirm Einstein's theory with extraordinary accuracy, they also extend its reach. Most tests of relativity involve weak gravitational fields, such as those near the Sun or binary pulsars. OJ-287, by contrast, operates in the strong field regime where space-time curvature is extreme. The agreement between prediction and measurement in this domain demonstrates that the same physical laws apply from the smallest scales to the largest. The quasar thus serves as a cosmic verification point, showing that even across billions of light-years the equations describing gravity remain exact. The precision achieved with OJ-287 allows astronomers to probe potential deviations from general relativity. By measuring how the timing of flares changes over decades, scientists can set limits on hypothetical phenomena, such as the existence of additional spatial dimensions alternative gravitational interactions or variations in the speed of light. So far, no deviations have been found. Every data point reinforces the conclusion that spacetime behaves exactly as predicted by Einstein's framework. Yet the ongoing observation of OJ-287 remains crucial, for as the orbit continues to shrink, the system enters regimes even more extreme where new physics might emerge. Thus, OJ-287 stands as a natural experiment running on cosmic timescales. It demonstrates that light, gravity, and time are inseparably linked, and that the universe's most violent environments obey the same laws that govern the motion of planets and the bending of light around stars. Each flare is not merely a luminous event but an equation written in light, confirming with every cycle that the structure of spacetime is both stable and knowable. In observing it, humanity witnesses the direct expression of relativity not as abstract theory, but as a living rhythm inscribed in the motions of black holes across the ages. The light of OJ-287 stretches across the entire electromagnetic spectrum from the longest radio waves to the highest energy gamma rays. Each wavelength reveals a different layer of the quasar's complex structure, helping astronomers build a composite image of the processes at work near its twin black holes. The optical light carries the most visible evidence of the periodic flares, but much of the underlying physics unfolds in wavelengths beyond human sight. By tracing these emissions together, scientists can map how energy travels through the system, from the dense disk where matter heats under gravity to the jets that blast particles into intergalactic space, to the radiation that ultimately reaches Earth. This multi-wavelength approach transforms the flickering of a distant point of light into a detailed chronicle of motion, temperature, and magnetic force operating near the edges of spacetime. At radio frequencies, OJ-287 is one of the brightest active galactic nuclei in the sky. Radio telescopes detect large-scale jets extending thousands of light-years from the galaxy's center, carrying streams of charged particles accelerated by magnetic fields. These jets are narrow, steady, and extraordinarily long-lived, suggesting a continuous flow of energy from the black hole's rotational power. Observations reveal that the jets are slightly curved, possibly due to precession of the central engine caused by the binary's orbital motion. When mapped over decades, small variations in the jet's direction correspond to the timing of optical flares, implying that disturbances in the disk propagate outward to affect the jet's base. In this way, the radio structure of OJ-287 acts as a distant mirror of its inner gravitational rhythm. Infrared observations probe regions of cooler dust surrounding the quasar. The intense radiation from the accretion disk heats nearby dust clouds, causing them to glow in mid-infrared wavelengths. Changes in this emission lag behind the optical flares by weeks or months, as the energy from the outburst travels outward and warms the surrounding environment. These delays provide direct measurements of distance within the quasar's inner structure. The infrared data also confirm that the energy released in each flare is sufficient to reconfigure the dust distribution, momentarily clearing paths through the torus that encircles the black hole. Over time, these changes create a dynamic cycle of heating and cooling that echoes the periodic behavior of the central engine. In the ultraviolet range, observations from space-based telescopes reveal details of the hottest regions of the disk and the aftermath of impact events. The ultraviolet light rises sharply during each flare, often preceding the visible peak, indicating that the first response to the secondary's passage occurs in the innermost, most energetic layers of plasma. These wavelengths carry information about the temperature and ionization state of the gas, showing that during outbursts the disk reaches tens of millions of degrees. The ultraviolet data, when combined with optical and X-ray observations, outline the energy cascade from the first compression shock to the gradual cooling that follows. X-rays mark the transition from visible heat to relativistic violence. They originate in the regions nearest the event horizon, where magnetic reconnection and particle collisions occur at extreme speeds. During flares, X-ray flux increases by several factors, often showing fine-scale variability on timescales of hours or less. These rapid fluctuations imply that the emitting region is small, only a few light hours across, and that its energy source is direct interaction between the secondary and the primary's disk. High-energy X-ray spectra reveal signatures of iron atoms stripped of nearly all electrons, evidence of temperatures high enough to destroy atomic structure itself. The behavior of these emissions confirms that the system operates in the strong gravity regime where time dilation, light bending, and Doppler effects all combine to shape the signal that reaches Earth. At even higher energies, OJ-287 emits gamma rays detected by orbiting observatories. These emissions come from particles within the jet accelerated to near the speed of light. When these particles collide with photons from the disk, they produce bursts of gamma radiation through a process known as inverse Compton scattering. The timing of these bursts often correlates with the optical flares, suggesting that disturbances in the disk feed directly into the jet's activity. The alignment of the jet toward Earth amplifies this emission, making OJ-287 one of the brightest sources in the gamma-ray sky during its active phases. Such alignment explains why its brightness can vary so dramatically with relatively minor physical changes near the core. The geometry of light and motion turns small fluctuations into cosmic beacons. The relationship between these different wavelengths reveals the flow of energy within the system. Optical light traces the immediate reaction of the disk. X-rays and gamma rays mark the conversion of mechanical energy into radiation. Radio waves record the slow transport of that energy outward through the jets. Together they describe a chain of events that begins deep near the event horizon and extends across thousands of light years. The timing between emissions at different wavelengths acts as a map of distances and processes, allowing astronomers to reconstruct how matter moves, heats, and radiates as it interacts with the binary black holes. Spectroscopic analysis across these bands provides further insight. Each wavelength carries absorption and emission lines, the fingerprints of atoms and ions moving at relativistic speeds. By measuring how these lines shift and broaden, astronomers deduce the velocities of the gas and the structure of the magnetic fields confining it. In OJ-287, these lines vary in both intensity and polarization during outbursts, confirming that the geometry of the emitting region changes as the secondary disturbs the disk. The direction of polarization rotates systematically following the evolution of magnetic fields that twist under gravitational stress. These patterns, consistent across multiple cycles, provide some of the clearest evidence of magnetic reconnection events triggered by the orbiting companion. Beyond the core, the radiation from OJ-287 interacts with its host galaxy and the intergalactic medium. The jets carrying enormous energy compress and heat, surrounding gas generating large radiolobes visible across millions of light years. These structures represent stored energy from countless cycles of activity, each flare contributing a tiny increment to the colossal reservoirs of relativistic particles that shape the galaxy's outer halo. Through these interactions, OJ-287 influences its entire environment, regulating the temperature and motion of gas that might otherwise form new stars. The quasar, though tiny in physical size relative to its host, exerts power on a galactic scale, connecting the physics of black holes to the evolution of galaxies. The multi-wavelength portrait of OJ287 reveals a system unified by gravity and illuminated by energy transformation. Each region disk jet halo plays a role in the transfer of matter and radiation. Observations across the spectrum confirm that these processes are synchronized by the binary's motion. The double flares in visible light coincide with changes in radio polarization, shifts in X-ray brightness, and pulses of gamma rays, all aligning with the secondary's predicted orbit. No other quasar has provided such a coherent multi-band confirmation of its internal mechanics. This coherence transforms OJ287 from a distant mystery into a precisely timed experiment in astrophysics, one that plays out over decades, yet adheres to rules written in the structure of spacetime itself. Through these layered observations, the system demonstrates how diverse forms of light can trace a single process. From radio to gamma, every photon escaping OJ287 tells a consistent story of energy, descending into gravity and re-emerging as radiation. The full spectrum is a translation of motion into light, a record of physical law expressed not in equations but in color and timing. When all wavelengths are assembled, the quasar ceases to be a flickering point in the sky and becomes a complete living structure, a symphony of radiation guided by the gravity of two black holes orbiting within a shared horizon of time. At the heart of OJ287, beyond the blinding light of the disk and the radiance of the jets, lies a region where time and gravity converge into something measurable, yet almost unimaginable, a flow of space-time itself. The jet is the most visible consequence of that inner structure, a narrow beam of matter and radiation propelled outward at nearly the speed of light. It emerges perpendicular to the plane of the accretion disk, tracing the axis of rotation of the primary black hole. Through it, energy extracted from rotation and magnetic fields is carried far beyond the confines of the galaxy. The jet is not a single stream, but a complex column of plasma threaded with magnetic lines that twist and coil as they travel outward. Within this flow, charged particles spiral along magnetic fields emitting synchrotron radiation that shines across radio-optical and X-ray bands. The jet's brightness changes subtly in sync with the binary's orbit, revealing that events deep within the accretion disk echo far into intergalactic space. The process that drives the jet begins near the event horizon, where the spinning black hole drags space-time around itself in a motion known as frame dragging. Magnetic fields anchored in the surrounding disk tap into this rotational energy, channeling it into powerful electromagnetic forces. These fields twist and tighten, accelerating plasma away from the black hole along open magnetic lines. The result is a pair of opposing jets that extend from both poles of the system, though only one is directed toward Earth. The apparent brightness of the approaching jet is amplified by relativistic beaming, a consequence of its high velocity and alignment with our line of sight. This effect makes OJ287 appear far brighter than it would otherwise be, turning a localized phenomenon into a beacon visible across billions of light-years. Observations of the jet reveal fine-scale changes in direction and brightness that correspond to the gravitational dance of the two black holes. As the secondary orbits its passage through the disk, perturbs the magnetic fields near the primary, altering the geometry of the jet's base. The orientation of the jet shifts slightly, producing long-term wobbles seen in radio maps. Over each 12-year cycle, these adjustments accumulate into a precession pattern that mirrors the binary orbit. By studying these variations, astronomers can deduce the alignment of the black hole's spins and the inclination of their orbit relative to Earth. In this way, the jet functions as a cosmic compass, pointing to the hidden choreography at the system's center. The energy released through the jet is immense. Each second OJ-287 expels particles and radiation equivalent to the combined luminosity of 100 galaxies. Yet this outflow is astonishingly narrow, confined to an angle of only a few degrees. Within this slender cone, plasma moves at nearly the speed of light, and magnetic turbulence shapes the emission into knots and filaments that can be tracked as they move outward. Radio interferometers capable of resolving fine detail have traced these structures over time, watching them drift away from the core. Each knot represents a burst of energy injected by changes in the accretion flow or magnetic field near the black hole. When the secondary plunges through the disk, a surge of material and magnetic reconnection triggers new knots linking the jet's behavior directly to the binary's motion. Within the jet, the balance between magnetic energy and particle motion determines its stability. Too much energy and the flow becomes chaotic. Too little and the beam dissipates. OJ-287's jet appears to maintain near-perfect equilibrium, remaining collimated for thousands of light-years. This balance suggests a steady engine at the core capable of sustaining its power over cosmic timescales. The jet's interaction with surrounding interstellar gas produces shocks that glow in radio wavelengths, forming vast lobes that mark the quasar's long-term activity. These lobes store the cumulative energy of countless outbursts, preserving a fossil record of the black hole's history stretching back millions of years. The polarization of light from OJ-287 provides additional clues about the magnetic structure within the jet. Polarization measures the alignment of electromagnetic waves, which depends on the orientation of magnetic fields at their source. Observations show that the degree of polarization varies cyclically, rising during optical flares and declining in quieter intervals. This correlation indicates that the magnetic fields are strengthened and reorganized when the secondary perturbs the disk. The pattern of rotation in polarization angle suggests a helical field structure consistent with theoretical models of magnetically launched jets. In effect, the binary's orbit not only controls the timing of flares, but also sculpts the electromagnetic architecture of the jet itself. X-ray and gamma-ray observations reveal that particles within the jet are accelerated to extraordinary energies. The mechanism of acceleration remains an open question, but most models invoke shock waves and magnetic reconnection as dominant processes. When the secondary black hole triggers a disturbance in the disk, it sends a pulse of energy into the magnetic field lines feeding the jet. These disturbances travel outward as waves, compressing and energizing the plasma. Electrons accelerated in this way emit synchrotron radiation in the radio and optical range, while their collisions with photons from the disk generate X-rays and gamma rays through inverse Compton scattering. This chain of events links the smallest scale gravitational interactions with the highest energy phenomena in the universe, illustrating the unity of processes across vast differences in scale. Despite its ferocity, the jet of OJ-287 operates with remarkable precision. Its alignment toward Earth has remained nearly constant for centuries, allowing astronomers to study its structure in detail. Slight oscillations in brightness correspond to the orbital phase of the secondary, confirming that the entire system acts as one coherent engine. During major outbursts, the jet brightens rapidly and then slowly fades as energy propagates outward. The delay between optical and radio peaks measures the time required for disturbances to travel from the inner disk to the outer jet, typically several months. These time delays form a kind of depth chart of the system, mapping the journey of energy from gravity to light. The scale of the jet underscores the immense efficiency of black holes as cosmic engines. A small fraction of the accreted matter is converted into energy with efficiency far surpassing any known physical process. In OJ287, this efficiency is enhanced by the interplay between the binary's motion and the primary's spin, which continuously stirs and recharges the magnetic fields. The result is a stable yet variable beam that has persisted for millions of years, radiating across intergalactic space and influencing the evolution of its host galaxy. The energy carried by the jet heat surrounding gas suppresses star formation and redistributes matter throughout the galactic halo. Thus, the system's behavior on scales of light-hours shapes structures spanning hundreds of thousands of light-years. In studying OJ287's jet, astronomers see not chaos but orchestration, a flow of matter governed by equations that connect magnetism, relativity, and fluid dynamics into one continuous system. Each photon emerging from the jet is a messenger from near the edge of a black hole's influence, carrying with it information about conditions where time and gravity are intertwined. Through decades of observation across wavelengths, the jet's fluctuations, orientation, and polarization have become as familiar as the flare cycle itself. Together they describe a single mechanism, gravity's capacity to convert rotation into light and motion into radiation, with elegance and precision that remain unmatched in the cosmos. OJ287's jet is therefore more than a feature of its structure. It is the visible spine of a system where two black holes and their environment move in concert, turning invisible forces into a continuous stream of measurable light that bridges the depths of time and space. Every orbit of OJ287 carries with it a slow leakage of energy through gravitational waves, a process invisible to telescopes but fundamental to the system's fate. These waves are distortions of space-time generated by the motion of the two black holes as they orbit each other. Like ripples spreading from a stone dropped into water, they travel outward at the speed of light, carrying away a fraction of the orbital energy. The amount lost during a single cycle is minuscule, yet over millions of years it accumulates, shrinking the orbit and drawing the two black holes ever closer together. This gradual decay explains why each 12-year flare pair arrives slightly earlier than predicted by classical mechanics. It is not coincidence, but the quiet consequence of gravity losing a tiny piece of itself to the fabric of the universe. Gravitational waves from OJ287 are far too low in frequency to be detected by ground-based observatories, which are designed to capture the brief high-pitched signals produced by the merger of stellar mass black holes or neutron stars. The waves from OJ287 are measured in microhertz, their cycles spanning months or years. Detecting such long-period signals requires entirely different instruments, vast networks of pulsars scattered across the galaxy, whose regular radio pulses can reveal passing distortions in space-time. These so-called pulsar timing arrays may one day register the slow heartbeat of OJ287's orbit, confirming directly what timing of its flares has already implied. Until then, astronomers rely on indirect evidence, the measured shortening of the orbital period, and the consistency of that change with predictions from Einstein's equations. The binary's gradual energy loss paints a portrait of a system evolving on cosmic timescales. Each orbit reduces the separation between the black holes by a fraction of a percent, bringing them infinitesimally closer to their eventual merger. The gravitational waves generated in this process carry staggering amounts of energy, equivalent to the output of countless stars, yet they spread so thinly across space that their effects are nearly imperceptible until they encounter matter or detectors. When the merger finally occurs tens of thousands of years from now, the event will release a flood of gravitational radiation powerful enough to outshine every star in the observable universe for a brief instant. That future signal travelling across space-time will one day reach distant observers as the final echo of OJ-287's long dance. Even before that end, the effects of orbital decay are evident in the system's current behaviour. The precession of the orbit increases as the separation narrows, altering the geometry of each disk crossing. Models show that in a few centuries the pattern of double flares may change entirely as the orbit tilts and the points of impact shift toward the inner disk. The regularity that has defined OJ-287 for over a century will give way to shorter, more intense cycles. Eventually the secondary will plunge so deep into the gravitational well that the disk crossings cease altogether, replaced by a final spiral toward coalescence. When that moment arrives, both black holes will merge into a single, even more massive body spinning rapidly and surrounded by the remnants of their former disk. The study of OJ-287's orbital decay provides one of the most direct ways to measure the emission of gravitational waves on supermassive scales. By comparing observed flare timings with predictions that include or exclude gravitational radiation, scientists can quantify the rate at which energy is being lost. The current measurements match the expected decay within a few percent, confirming that general relativity applies across distances of billions of light-years and for masses far exceeding anything found within the Milky Way. This result also places constraints on alternative theories of gravity that predict different energy loss rates. So far, OJ-287 has proven an unwavering supporter of Einstein's view of space-time. The gravitational waves from OJ-287 do more than shrink the orbit. They also carry information about the masses and spins of both black holes. As the orbit changes, the pattern of wave emission shifts, encoding details about the system's configuration. Though undetectable for now, these signals could one day be resolved by next-generation space observatories. Missions such as the planned Laser Interferometer Space Antenna will be sensitive to the low-frequency regime of supermassive binaries, potentially allowing direct detection of OJ-287's space-time tremors. Such observations would transform the system from a source of indirect evidence into a fully observed gravitational laboratory, bridging the gap between electromagnetic astronomy and the emerging field of gravitational astrophysics. Within the galaxy hosting OJ-287, the gradual decay of the binary's orbit influences the surrounding environment in subtle but far-reaching ways. As the black holes spiral inward, their combined gravitational potential well deepens, pulling nearby gas and stars slightly closer. This compression heats the interstellar medium and alters the distribution of matter around the nucleus. Over time, the constant outflow of energy through radiation and jets balances this inflow, maintaining a kind of dynamic equilibrium. The galaxy remains stable while its core evolves toward eventual unification. In this sense, the orbital decay is not a collapse, but a process of cosmic reconfiguration in which gravity slowly simplifies what time has complicated. The merging of such black holes is a critical stage in galactic evolution. When galaxies collide, their central black holes eventually pair and spiral inward, as OJ-287 demonstrates. The gravitational waves produced in these events help shape the large-scale structure of the universe by redistributing energy and influencing how galaxies cluster together. OJ-207 thus serves as a prototype for a process that has occurred countless times throughout cosmic history. Its current phase, stable but shrinking, represents a middle stage between violent galactic merger and the quiet final state of a single massive nucleus. By observing it, astronomers witness a link in the chain of evolution that connects early cosmic formation to present-day structure. Theoretical models suggest that when OJ-287 finally merges, the resulting black hole will spin rapidly and emit a brief but intense burst of light As remaining gas and magnetic fields reorganize, the jet may realign or restart in a new direction, sending a fresh beam of radiation into space. The surrounding galaxy will briefly brighten before settling into calm. Though this final act will occur long after human observation ends, its inevitability is written in the mathematics of the system. Each flare we observe today is both a sign of ongoing activity and a countdown toward that conclusion. The orbit is a cosmic clock winding down by imperceptible increments, its ticking marked in centuries rather than seconds. For now, the binary continues its slow spiral, radiating both light and gravity in harmony. The energy lost through gravitational waves is balanced by the energy gained from infalling matter, creating a stable configuration that may persist for thousands of more cycles. The pattern of flares, the shifting of the orbit, and the faint gravitational tremor extending through space all reflect a single principle: that energy once set in motion by gravity cannot rest until it finds balance. OJ-287 demonstrates this balance with perfection. It transforms orbital motion into light, and light into evidence, showing how even in the vastness of space, the laws of physics remain exact and continuous. The gradual decay of OJ-287's orbit represents one of the universe's most patient stories, a slow exchange of energy between matter and space-time itself. Each flare we record is both illumination and farewell, a photon's flight across billions of years, carrying the record of a system that is forever changing yet constant in its obedience to law. The binary black holes of OJ-287 locked in their shrinking orbit continue to demonstrate that gravity, though silent, writes its own narrative in light and time, a narrative of motion that will one day end in stillness when two separate horizons merge into one. Every flare of OJ-287, every pulse of light and faint echo of gravitational energy also carries a record of time itself. The system operates on scales so immense that the familiar rhythm of seconds, minutes, and years becomes meaningless. Here one orbit lasts 12 Earth years yet for gas circling near the event horizon. Time flows so differently that a few minutes may encompass that same interval. In this layered landscape of time, the quasar becomes a living demonstration of relativity, showing that duration and sequence are not universal, but depend on gravity's influence. When astronomers compare light from the outer regions of the accretion disk with that from the inner zones, they're effectively comparing different clocks within the same system. The differences are minute yet measurable, confirming that time dilates as gravity strengthens, and that energy radiating from the innermost orbit is stretched by its climb out of the gravitational well. Each photon redshifted by its journey becomes a witness to the distortion of time itself. At the human scale, these relativistic effects are invisible, but over billions of years they shape how OJ-287 evolves. The secondary black hole's orbit does not merely trace space. It loops through time, curving around the primary in a geometry that ties motion and duration together. As the secondary approaches the disk, it experiences a gravitational time dilation so strong that its internal clock slows relative to distant observers. To us, this manifests as a precise pattern in the flare, timing a regularity that persists even as the orbit decays. The predictability of these flares is not a contradiction to relativity, but a proof of it. The curvature of time does not destroy order, it defines it. The very structure of the system's periodicity emerges from spacetime's geometry, not despite it. The quasar's constancy over cosmic time offers a rare opportunity to explore how large-scale systems maintain coherence, despite relativistic conditions. For the disk, the flow of gas inward is steady but not uniform. Clumps and filaments of plasma orbit the black hole on timescales of hours or days, yet from Earth their light blends into a continuous glow. Only during flares does the pattern break, revealing how time near the event horizon compresses and stretches. Observations of rapid flickering within the optical and X-ray data suggest that regions near the black hole fluctuate faster than time should allow, but when corrected for relativistic effects, these variations fit precisely within theoretical limits. In this way, OJ-287 serves as both a demonstration and a calibration of time dilation in an environment that cannot be replicated in laboratories. Time also shapes how energy moves through the system. As matter spirals inward, it radiates away angular momentum, releasing light that escapes only because time itself flows differently at each radius. Closer to the black hole, processes occur in slow motion relative to the outer disk, yet the light they emit reaches us in order layered across the years it takes to cross interstellar space. When astronomers stack these emissions over decades of monitoring, they build not just a light curve but a timeline, a record of moments in the life of a quasar spread out across cosmic distance. OJ-287's pattern of double flares repeats not merely in space but in time, as though the system were striking the same chord in a symphony that began long before Earth formed. The influence of time extends beyond the binary itself. The jets carrying plasma at near light speeds preserve a memory of conditions at the moment they were launched. As these beams propagate into intergalactic space, they stretch and fade, but their internal structure reveals the rhythm of the engine that created them. Knots observed thousands of light-years from the core correspond to outbursts that occurred centuries earlier in the galaxy's frame of reference. By tracing these features backward, astronomers can reconstruct a historical record of OJ-287's activity, effectively looking into its past along the length of its jet. In this way, the quasar becomes a time machine of its own, making its light a continuous archive of motion, gravity, and decay. The temporal precision of OJ-287 has inspired comparisons to the most stable clocks ever built by humans. Its regularity rivals the accuracy of atomic timekeeping when scaled to its natural period. The difference between predicted and observed flare timings is often less than a few days out of decades, an error smaller than 1 part in 1,000. This stability allows scientists to measure tiny changes in the orbit and to infer how gravity and time evolved together. In effect, OJ-287 is both a clock and a calendar, written in light 1 that records not the passing of seasons, but the gradual unfolding of cosmic history. It tells time not for humans, but for the universe itself. The curvature of space-time near the primary black hole also introduces a phenomenon known as gravitational lensing. Light from the accretion disk and the impact flares bends around the central mass, reaching Earth along multiple paths. Some rays travel directly, others loop around the black hole before escaping, arriving slightly later. These delays, often measured in hours or days, provide another means of studying time in curved space. By analyzing how the intensity of light changes over these intervals, astronomers can reconstruct the shape of space-time near the event horizon. The results confirm what relativity predicts: time slows and space folds in precise proportion to mass. As the binary system continues its slow spiral inward, the geometry of its orbits will alter the sequence of flares. The next century may see the intervals between outbursts shorten the order of double peak shift and the brightness ratios change. These developments will provide even more opportunities to study time's curvature at high precision. Each alteration will reflect not randomness, but the evolving relationship between motion and space-time. The data from OJ-287 will allow scientists to refine models of how time behaves under gravity's most intense conditions, improving predictions for systems that will one day merge and produce detectable gravitational waves. The quasar's light does not only reveal physical time, but also cosmic time, the broader context of the universe's expansion. The photons we detect today left OJ 287 billions of years ago when the universe was younger and denser. As they travelled, the expansion of space stretched their wavelengths, embedding in them a record of cosmic history. The redshift measured in OJ 287's spectrum tells us how fast the universe has grown since those photons began their journey. Thus, every observation of its flares also serves as a measurement of the cosmos itself, linking local time near the black hole to universal time across all of space. In contemplating OJ 287, astronomers see how the universe keeps its own layered clocks. There is the local time of orbiting plasma, the systemic time of the binary's 12-year cycle, and the cosmological time of billions of years between emission and detection. Each of these scales flows differently, yet all remain connected through gravity's unchanging rules. The coherence among them demonstrates that time is not chaotic, but structured even under the strain of black holes. OJ 287's repeating light confirms that order persists where we might expect only distortion, and that the universe, however vast, follows patterns that can be measured and understood. Thus, within its rhythmic flashes, OJ 287 holds a lesson about the nature of time. It shows that time is not merely a backdrop against which events unfold, but a participant in every process stretched and shaped by gravity yet never broken. The binary's periodic light is the visible form of time itself, bending and returning a cosmic pendulum, marking intervals that bridge the gap between moments and eternity. Each flare we observe today left its origin before life existed on Earth, yet it arrives now with precision that defies the ages. OJ 287 continues to count cycle by cycle, a record of time written in light that will endure until the two black holes finally merge and the last beat of their cosmic clock fades into the quiet of a single unbroken horizon. Long before humanity turned telescopes toward the sky, the drama of OJ 287 had already been unfolding in silence, its light crossing space on a journey of billions of years. The photons that reach Earth now began their travel when the Milky Way was still young, carrying information from a time when galaxies were colliding more frequently, and the universe's structure was still taking shape. In that distant era, the host galaxy of OJ 287 had already settled into the massive elliptical form it holds today, with its central black hole dominating the surrounding stars and gas. The processes we observe in the present, the flares, the jets, the precession, and the gradual spiral of the binary, have been repeating for untold eons, continuing through cycles of cosmic expansion. The quasar's story is not confined to decades of human observation, but extends across geological and astronomical time-bridging epochs of star formation and extinction alike. The long view reveals OJ 287 as a product of galactic evolution. Its parent galaxy likely formed through the merger of several massive progenitors, each carrying its own central black hole. When those galaxies collided, their black holes sank toward the new center through gravitational interactions, eventually forming the binary we observe today. Over billions of years, the orbit of the secondary shrank through interactions with stars and gas, until gravitational radiation took over as the dominant braking force. The periodic flares we see now represent the final observable stage of a process that began when the universe was only a fraction of its current age. In this sense, OJ 287 is not only an object of present study, but also a fossil record of cosmic history, preserving in its light the memory of galactic formation and gravitational evolution. The environment around OJ 287 bears the marks of this long past. The host galaxy, though faint, glows in near-infrared surveys as a diffuse halo of old stars. It lacks the spiral structure and star-forming regions typical of younger systems, suggesting that most of its stellar population formed billions of years ago and has since aged into quiet stability. Yet at its centre, the quasar remains intensely active, indicating that the black holes have continued to accrete gas long after the rest of the galaxy became dormant. The source of this fuel may be the debris of earlier mergers, or the slow inflow of intergalactic gas along filaments of the cosmic web. However it arrives, this material sustains the luminous engine that allows OJ-287 to remain visible across the universe. On such timescales, even the slow drift of the binary's orbit becomes significant. Each revolution of 12 years on Earth corresponds to millions of revolutions since the pair first became bound. Over this immense sequence of cycles, the system has maintained its rhythm, adjusting only as relativity dictates. This endurance demonstrates the stability of physical law across all of time. The same equations that describe the motion of planets around the Sun govern the motion of black holes separated by billions of light years. The constants of nature have not changed. The rules written at the universe's birth continue to shape events even now. OJ-287, through its regularity, is a monument to this constancy, a light that proves the permanence of order in a universe of change. The photons we detect today have crossed a universe that has itself expanded during their journey. They have travelled through cosmic epochs marked by the formation of clusters, the ignition of quasars, and the cooling of the cosmic microwave background. Along the way, they have been stretched by the expansion of space, their wavelengths elongated into red-shifted tones that encode the age and distance of their origin. When astronomers measure this redshift, they are not only locating OJ-287 in space, but also in time, pinpointing a moment billions of years in the past. The quasar therefore offers a glimpse of what the universe was like long before the solar system existed, allowing scientists to connect the behaviour of modern black holes with the conditions of the early cosmos. Because OJ-287 is so distant, its light has passed through vast regions of intergalactic gas and dust. Along the way, it has been subtly absorbed and re-emitted, creating faint imprints in its spectrum that reveal the composition of matter between galaxies. These absorption lines show traces of hydrogen, helium, and heavier elements, the scattered residue of ancient stars that exploded long before our own sun was born. Thus, every observation of OJ-287 also samples the intergalactic medium itself, turning the quasar into a probe for studying the evolution of cosmic matter. Its photons, in passing through billions of light-years of space, collect the signatures of countless unseen worlds, transforming a single point of light into a record of everything it has crossed. The vast timescale of OJ-287's story emphasizes how the universe preserves continuity, even amid constant transformation. While the two black holes orbit and emit their rhythmic flares, the galaxies around them drift farther apart through cosmic expansion. Yet to observers on Earth, the timing of OJ-287's flares remains predictable, unaltered by the stretching of space that separates all galaxies. This constancy arises because the laws of gravity are scale-independent. They operate with the same precision across the smallest atoms and the largest structures. The repeating light of OJ-287 therefore embodies not only a specific cosmic event, but also the broader principle that the universe itself is coherent, that its changes unfold within an unchanging framework of physical law. For astronomers, this persistence transforms OJ-287 into a benchmark for understanding both individual galaxies and the universe as a whole. By studying how its light changes with distance and redshift, scientists calibrate models of cosmic expansion and refine estimates of how supermassive black holes evolve through time. Each flare provides a fixed reference point against which to measure cosmic evolution. Over decades of observation, these data feed into a wider picture of how energy and structure have developed since the early universe. In a sense, OJ-287 is not just an isolated quasar, but part of the metronome that keeps cosmic history in measure. The endurance of OJ-287's rhythm over billions of years also carries implications for the ultimate fate of energy in the universe. Each flare converts gravitational potential into light, dispersing a small amount of order into the expanding cosmos. As these photons travel outward, they contribute to the slow diffusion of energy that will one day lead to universal equilibrium, the distant state of heat death, where no gradients remain to power motion or light. Though that future lies far beyond imagination, OJ-287 reminds us that every luminous event participates in it, that even beauty and order are transient forms within a greater continuity. The quasar's steady brightness becomes a meditation on impermanence, a signal born in violence that endures through calm, carrying the memory of motion, long after the causes have changed. The story of OJ-287, when stretched across cosmic time, is both precise and eternal. It shows that while the scale of the universe dwarfs all human comprehension, its processes obey rules that remain simple and consistent. Matter falls energy, radiates orbits, decay, and light travels outward indifferent to the passage of eras. Through its unbroken sequence of flares, OJ-287 links the present moment to a deep past and an even deeper future, illustrating how a single gravitational system can embody the structure of cosmic time itself. The photons that arrive tonight will continue to reach Earth for millennia, each one a fragment of a pattern, older than life, carrying across the darkness the enduring rhythm of gravity, motion and light that defines this binary black hole at the heart of a quiet galaxy in Cancer. In the quiet intervals between its predictable flares, OJ-287 returns to a state of calm luminosity, a steady beacon whose faint, constant glow masks the turmoil within. This background emission, produced by the steady inflow of gas into the primary black hole's accretion disk, provides a continuous context for the violent outbursts that punctuate its rhythm. Even in its so-called resting phase, the quasar radiates with the power of trillions of suns sustained by the simple and eternal act of gravity turning motion into light. These long quiet spans allow astronomers to observe the underlying mechanisms of stability, how magnetic fields, temperature gradients and orbital motion balance into a dynamic equilibrium that can persist for millions of years. In this phase, OJ-287 embodies the steady order underlying cosmic chaos, a self-regulating engine that converts matter into energy with the same precision year after year. The quasar's calm phases reveal details invisible during the brilliance of its flares. High-resolution spectroscopy shows narrow emission lines from cooler gas, orbiting farther from the black hole, tracing the outer edge of the accretion disk and the surrounding broad-line region. This gas forms a complex halo extending light-years into space, illuminated by the central radiation source. Subtle changes in these lines across the 12-year cycle reveal how energy from each flare propagates outward, heating and ionizing the environment before fading again. The result is a kind of slow echo, a record of light reverberating through the surrounding matter. The speed and pattern of these echoes help astronomers map the structure of the inner galaxy, just as sound reflections map the contours of a distant cave. During these quiescent intervals, the secondary black hole travels through the outer reaches of its orbit, moving far from the disk's plane and leaving the system temporarily undisturbed. Even at its most distant, however, the smaller black hole exerts a steady gravitational influence on the primary, causing slight oscillations in the disk's structure and modulating the flow of material toward the center. These variations appear as gentle, almost imperceptible fluctuations in brightness, a faint breathing pattern underlying the grander pulses of the flare cycle. This continuous modulation connects the quiet and active phases into a single unbroken process, showing that the system never truly rests. It only shifts between modes of equilibrium and disruption. Observing OJ-287 in its subdued state also deepens understanding of the long-term evolution of active galactic nuclei. In most galaxies, such activity fades as the supply of accreting gas diminishes, leaving behind a dormant black hole. But OJ-287 remains alive, its binary nature continually stirring the disk and replenishing it with fresh material. This sustained feeding prevents stagnation, ensuring that the quasar remains active while others of its age have gone dark. Its persistence suggests that binary black holes may prolong the lifetimes of galactic cores, maintaining their luminosity long after solitary systems would have faded. In this way, OJ-287 offers a glimpse into the processes that keep certain galaxies radiant while others fall silent. The quasar's continuous monitoring over decades has transformed it from a curiosity into a keystone for multiple fields of astrophysics. It serves as a calibration point for instruments, a testbed for theories of relativity, and a model for understanding how galaxies and their black holes co-evolve. Every wavelength from radio to gamma rays contributes data that refine estimates of mass spin, magnetic field strength, and orbital dynamics. The precision achieved through these observations has elevated OJ-287 into a natural standard, a cosmic clock whose reliability allows scientists to measure changes in space-time itself. Its consistency across centuries demonstrates that the fundamental laws of nature are indeed invariant, that gravity behaves the same in the distant universe as it does near Earth. Even as technology advances, OJ-287 continues to challenge perception. Instruments capable of detecting polarization at unprecedented sensitivity now trace the smallest shifts in magnetic field orientation during flares, while very long baseline interferometry reveals jet structures on scales smaller than a single light year. Each improvement brings the system into sharper focus, yet the essential mystery remains two invisible masses bound in a dance that transforms darkness into radiance. What began as flickering light on a photographic plate has evolved into a complex portrait of forces shaping the universe. The binary black hole, though unreachable, becomes familiar through its rhythm, its light as regular as a pulse, and as distant as time itself. Between each pair of flares, the disk reforms. Gas stripped from previous impacts gradually settles into circular orbits, again cooling and reorganizing into its layered structure. Dust condenses at the outer edge, magnetic fields realign, and radiation pressure balances gravitational pull. The system rebuilds itself, preparing for the next disturbance. In this regeneration lies the essence of OJ-287's stability destruction and renewal alternating in perpetual rhythm. This cycle mirrors the broader processes of the universe, where collapse and creation are inseparable, each sustaining the other. Every flare consumes a little more material, every calm phase gathers new fuel, and the pattern continues as it has for billions of years. Beyond its physical details, OJ-287 has come to symbolize endurance. The constancy of its rhythm across cosmic distances underscores a simple truth that the universe, vast and indifferent though it may seem, operates with quiet precision. Each photon leaving the quasar carries information encoded by gravity and time, arriving on Earth billions of years later, to reveal that the same equations still hold. The binary system is both a relic of the early cosmos and an ongoing experiment, its behavior confirming what physics predicts even in the strongest gravitational fields. Through it, we glimpse not only the mechanics of black holes, but the stability of natural law itself. The quiet luminosity that fills the long years between flares thus holds as much meaning as the eruptions themselves. It demonstrates that equilibrium is not stasis, but the balancing of constant motion. Even in its calm, OJ-287 remains alive with slow processes, magnetic fields shifting particles orbiting radiation flowing outward at the speed of light. These hidden movements ensure that the next flare will come on schedule as inevitable as the orbit that drives it. The system's constancy reassures astronomers that despite the vastness of space and time, nature is knowable and repeatable. What we witness in OJ-287 is not randomness, but order so deep it extends beyond our lifespans and civilizations. As the current epoch of observation continues, OJ-287 will remain a guidepost in the expanding universe. Its light, constant and rhythmic, connects past and future across billions of years. The binary's quiet intervals teach patience, its flares teach precision, and its enduring regularity teaches trust in the fabric of reality. In every phase, active or calm, bright or dim, the system affirms that the universe is not chaos, but an intricate design governed by rules that do not falter. To observe OJ-287 is to witness permanence expressed through motion, an endless balance between gravity and light. The calm between its flares is the heartbeat between breaths, the silent interval through which the cosmos reminds itself that even the most violent systems can achieve harmony through time.